and this needs to be positive decreasing continuous on this interval from wherever to infinity. Okay, does that make sense? So this converges if and only if this converges. So in particular, this diverges if and only if that diverges. So for instance, if I ask, does the sum of 1 over n squared plus 1 from say 1 to infinity converge or diverge? Converges, right. It's a yes, the integral world you can do a p-test. Also, you could integrate it with arctan, right? So first of all, does the integral test apply? Is it a positive, continuous, and decreasing function? Yeah, what? So it's positive, obviously. It's continuous. The denominator is never 0. Polynomial over polynomial, denominator is never 0. That's it, continuous. But why is it decreasing? Yeah, n grows, the denominator grows, so the thing gets smaller and smaller. Or if you like, the function we're talking about here, so we're trying to compare it to the function 1 over x squared plus 1 dx. And since n is going from 1 to infinity, this integral should go from 1 to infinity. And this function 1 over x squared, so f of x here is the function 1 over, if you like, 1 plus x squared, and f prime is this to the minus 1, so it's minus 1 plus x squared to the minus 2 times 2x by a chain rule, right? And x is positive from 1 to infinity, so it's a negative number. So this is negative, meaning when your derivative is negative, you're decreasing. So you can also look at this and say the function is decreasing. It's obviously positive and it's continuous. So you can compare this series to this integral. And this integral we know is, well, it's arctan something like this, right? And that is pi over 2 minus pi over 4, which is pi over 4. So that integral is finite, meaning it converges. So therefore this series converges. We're not saying this series adds up to pi over 4, it's just that this series will converge. We don't know if it will converge to something more or less than pi over 4. It's just that it will converge. Okay, so there is no relation in the values. It's just there is a relation in convergence. Both converge or both times. You take your series, turn it into the same integral, where every n becomes, or I or k or whatever it is, becomes an x or a y or a p. Yeah. So that was the integral test. You can compare your series to the corresponding integral, and they will either both converge or both diverge. But you have to test, is the function decreasing and positive and continuous? Eventually. It needs to be eventually decreasing, eventually positive and continuous. So this also gives us for free the p-test for series. Meaning if you have the series 1 over n to the p, n from say 1 to infinity, anything other than 0, really it could go from 2 to infinity, 5 to infinity, 10 to infinity. It's not like minus 1 to infinity, because then you have 1 over 0. It's, well, you know, if p is positive, then this is decreasing and continuous. And what else do I need to do? Positive, decreasing, and continuous. Yeah, it's positive and decreasing and continuous. So you can compare it to the corresponding p-test integral, right? Which converges when? Yeah, so this converges when p is greater than 1. And so this series also converges for p greater than 1 and diverges for sure for p less or equal to 1, even p negative. I mean, obviously, when p is 0, you get 1 plus 1 plus 1 plus 1, that diverges. If p is negative, this is really in the numerator, and you're adding bigger and bigger things, so that diverges. So it's just literally only converges exactly when p is bigger than 1 and diverges. And so you just get a p-test for sums. And now we'll also use this p-test for sums as the way we were using the p-test integrals for integral convergence. Now we'll use it for sums. Yeah, so let's do just one more example. Hold on. This is great, isn't it? Okay, so you know, this is the integral test. It's on the sheet somewhere near the bottom because I put the sheet in order of things that you should try first. Once confronted with the series, what should you do first? Right? You should first try divergence test and then so on. So let's say you have the series log n over n from 1 to infinity. So it starts 0 plus log 2 over 2 plus log 3 over 3 plus log 4 over 4. It goes on forever. Does it converge? I mean, I don't know. So let's see. So how do you test this? So it's positive, decreasing, continuous, which means we can use the integral test. That doesn't mean it's converging. It just means that we can do a test. So it is positive because log is positive after 1, and it's continuous because log is continuous for all positive numbers, and we're never dividing by 0. And it's decreasing. Well, why is it decreasing? Well, we have the function log x over x. Take its derivative, and you get something like so you have basically 1 minus log x over x squared, which is negative for x bigger than 1. This is negative because log is going to be bigger than 1. No, sorry, after e it's negative. This is negative after e. After e, I mean for x bigger than e. So it's eventually decreasing, right? That's good enough for us. So that means this can be compared to the integral of log x over x dx from 1 to infinity. Right? So now you can compare them. Yeah, you have to go from 1 to e and then from e to infinity. But that part from 1 to e is some finite number. It won't affect our conversion. Yeah, so basically when something is eventually continuous and decreasing in positive, you can just use the integral test. Unless your finitely many terms in the beginning already are infinite. Right? So, and how do you do this integral? This is also like the first u sub. Yeah, log becomes u. 1 over x dx is du. So it's integral of u du. which is u squared over 2. So it's log x squared over 2 from 1 to infinity, meaning it's the limit as t goes to infinity of log t squared. That's it. But that limit is what? It's infinity. So this integral diverges, and therefore that sum also diverges by the integral test, right? This thing also diverges. Because what the integral test says, these two, if it's a continuous positive decreasing function, then the sum and the integral may either both diverge or both converge. Yeah. Yes. Yeah, it should start from you. Yes. So we should have log 1 over 1 plus log 2 over 2 plus the rest of it from 3 to infinity, right? And then that compares to the integral from 3 to infinity of log x over x. But this bit from 1 to 3, that's a finite number. That's a number because this is a continuous function from 1 to x. On a compact interval, a continuous function integral is a finite number. There's nothing blowing up, we're not going to infinity, we're not doing any improper stuff here. So that's why I just took it from 1 to infinity. It's okay. And I'll be grading your exam, so it's okay. If someone else saw this, maybe they would be like, hey, technically that's not exactly 100% how you should do it, but it literally does not change a thing. As long as it's eventually positive, decreasing, and continuous, you can just apply the integral test. Yeah. Why would we do what? Well, we need to figure out if that. So the thing is, the integral test only tells you that a series is comparable to an integral if that function in the integral, or the function in the series, is positive, decreasing, and continuous. And it's only decreasing after e. So it's not decreasing up to 2. It may be increasing up to 2. It is increasing up to 2. And then it starts decreasing after that. Right, so from here on, it's decreasing. So that bit is comparable to the integral. So to know if this sum, this infinite sum, is finite or not, you have to check if this infinite integral is finite or not. And it is. This one is infinite. Or suppose your integral was finite. It doesn't matter if it's finite or infinite. This one will be finite or infinite accordingly. Then adding a couple of terms or adding a finite number to it doesn't change the fact that it's finite or infinite. Either way, this is finite and that's finite, or this is infinite and that's infinite. Yes. Technically, yeah, you cannot apply the integral test unless it is decreasing, and it's decreasing from here. But I just applied it here because the first two terms, that's a finite thing you're adding. Either you still get infinity or still get something finite. It doesn't change. Yeah. Yeah. Sorry? In the integral bit? No. Even these are not related. It's just their values are not the same. It's just that they're either both infinite or both finite. If they're finite, they're not the same finite number. They are different. This is that's what this is, and this one is the area up to 3 from 1 to 3. Yeah. Okay, that's a good segue into what we're trying to do next. So remember, we also talked about tails of series last time, right? You have a series and you add it to a partial sum, some nth term. Then after that term, so I'll erase this. And so I have some series a, and maybe n starts from 5, or let's go from minus 2 to infinity. So it's a sub minus 2, a sub minus 1, a sub 0, a sub 1, a sub 2, so to infinity. Actually, I shouldn't have maybe done that. But anyway, if you take a partial sum, like the third partial sum here, or maybe we could call it the 0th partial sum here, or the first partial sum like this, it's just you add up the first few terms up to that index. Then what's left over is the corresponding remainder. Right? Yes? So, for instance, here this will be the 0th remainder. Here this would be the first partial sum and the first remainder. Right? So if you have a series that's going off to infinity, and all the terms are getting smaller and smaller, and you're adding them, and yet you get a finite number. So it's a series that converges. Then you don't really need to add up to infinity to get a good estimate of what the answer is. If you add up to, say, 100 terms, you're pretty close to what the answer should be. Because afterwards, it should be a tiny amount, given that the whole thing converges to infinity. Right? So the next thing is, how do you estimate how close you are to the actual answer? By just adding a few terms in this integral test scenario. And it's surprisingly nice, the answer. It's not too bad. So remember, on the quiz on Thursday, I'll ask you a question like, how many terms of this series do you need to estimate within 0.001? So how do you do that? Kind of question, right? So let's think of, again, let's start from 0, so or 1. Again, so let's say I have some value a1 at 1, and then I have some value a2, some value a3. It doesn't matter, but actually it will only work if it's eventually decreasing, so let's stick to that. So I have 2, 3, 4, and then eventually you get to a point where it's at n plus 1, n plus 2, and so on. If I add up everything until the nth term, so I add up everything up to here, the nth partial sum, then what's left over is this n plus first, it's the nth remainder, right? Actually, hold on, let me make it better. Bigger picture. So let's say here at n here, and n plus 1 here, and then dot dot dot. So this is all the an's, the heights of these are part of some function. So if I take the right endpoint estimates of all these rectangles, if I take this estimate for all of these rectangles here. And look at the areas under here. Those areas are not the first one, right? Let me just check to see. Yeah. Yeah. Basically, this is the function f of x. Right? Let's forget about this sum for a second, and let's have a corresponding picture. At n I have this value, n plus 1 I have this value, plus 2 I have this value, so this is 3. And these are part of this function, which is positive, decreasing, and continuous. And what I could do is take the left endpoint approximation for all of these instead. Like this. I could take the right endpoints for each of the rectangles, or I could take the left endpoints for each rectangle. In either case, the shaded bit here sorry, I do need this here. So then the shaded bit here is n plus 1 plus n plus 2 plus n plus 3, right? So this area is n plus 1, this area is n plus 2, I'm sorry, a sub n plus 1, a sub n plus 2, right? Okay, so I took the height at n plus 1, so that's a sub n plus 1, but this width is 1, so this area is a sub n plus 1. Yes? Are you following this? I'm having a hard time getting my mind around this. It's nothing complicated, it's trivial. So this area here is a sub n plus 1, this area is a sub n plus 2, this is a sub n plus 3. Why is this one n plus 2? Well, because its width is 1 and its height is the value at n plus 2, which is a sub n plus 2. So this height is a sub n plus 2 times 1, so that area is a sub n plus 2, and so on. These rectangular boxes, the shaded area here is the sum from n plus 1 to infinity of a sub n, which is in fact the nth remainder. If you take the sum up to n terms, the nth remainder is the rest of the series from n plus 1 to infinity, right? Also, this shaded region here is also the nth remainder, because this rectangle has area a sub n plus 1, whereas this one has area n plus 2, this one has area a sub n plus 3, and so on. So it's also the sum, right? So this is the sum starting from n plus 1, then n plus 2, then dot dot dot. And this is also the sum. This shaded area here is also the sum a sub n plus 1 and then n plus 2. So they're the same sum. The shaded area up there and the shaded area down here, they're the same exact number. Yeah, exactly. So one of them is an underestimate, the other one is an overestimate of the curve. Because one of them starts at n plus 1, but the other one starts at n. It's like you take this shaded bit, shift it to the left 1 unit, and it will be a perfect fit on the curve with its right endpoints. and you'll get this picture. Or you can take this picture and shift it to the right by 1 unit, shift all the shaded bits to the right, and all these rectangles will also perfectly fit on the curve, but with their left endpoints, because the left endpoints meet the right endpoints once you shift to the right. So the shaded bit here and the shaded bit here is exactly the same area, and in fact both of them represent the nth remainder, Rn. But from this picture it's clear that this Rn is actually less than the integral of f from n to infinity. Because like you said, it's an underestimate for the area. So if I take the integral from n to infinity of f of x, I get something that's more than r sub n. But here, if I take the integral from n plus 1 to infinity of f of x, that integral, meaning the area under the curve, is less than the boxes. And the boxes are Rn, so I get something less than Rn. Yeah? In this case, because I want these to be the same, right? I want these areas to be both Rn. Yeah, because the area of this one would be a sub n, which is already, so let me remind everyone in the normal setting what it is. So a1, a2, up to an, that sum is the nth partial sum, and then the rest of it from n plus 1 to infinity, that's the nth remainder. Right? So, and this is the sum we want, n plus 1, n plus 2, n plus 3. And this is a sub n plus 1, n plus 2, n plus 3, and so on. But this is also a sub n plus 1, n plus 2, n plus 3. This would be a sub n, which is the last term of Sn. We don't want that term in the nth remainder. It's part of the nth partial sum. So the nth remainder, either way, the nth remainder is less or more than certain integrals, and it's less than the integral from n to infinity, but it's more than the integral from n plus 1. That's the integral S. Okay, this is not, I mean, it looks complicated, but what do we just establish? That if you take the integral from n plus 1 to infinity of f of x, you get something less, or let's say equal. I don't want to take a risk here. Than the nth remainder, which is less or equal than the integral from n than the integral from n to infinity of f. Okay, and this is the thing you need to remember for the estimate. So let's forget about the rest of it. Okay. So, meaning, if I add 100 terms, the leftover bit of the series, if I add the first 100 terms in the series, the leftover bit is less than the integral from 100 to infinity. The leftover bit is less than the integral from 100 to infinity, which is an integral, and you can maybe even estimate. So if I get this thing to be less than, say, 0.1, then I know that I'm within 0.1 of the actual answer. Okay? So if I add, so let's take an example. Yeah. So let's say estimate the sum of 1 over n cubed from 1 to infinity using 10 terms, right? and see how far we are from the actual answer. Right? So in other words, we take, instead of the infinite sum, we take 1 over 1 cube, 1 over 2 cube. So 1 cube is 1, 2 cube is 8, 3 cube is 27, 4 cube is 64, 5 cube is 125, and then what's 6 cube? 216. 7 cube I remember, yeah. And then 8 cube? 729. And then the 10 cube is 1000. So instead of going dot dot dot, you just add the first 10 terms. And you say, well, you know what, that's probably good enough to get to the actual answer you get by adding all the infinity menu. So now you can add this. It's only 10 terms, you add them on your calculator. There you go. It's like 1 point. This is what I have in the notebook, so you can check if that's correct or not. Is that correct? Yeah? So you add the first 10. You don't add all the infinity many. And you say, what, am I close to the answer? Is this like good up to 2 digits and then I don't know, or is the actual answer like 52 and I'm at 1.1 or something? Like how far am I from the answer, from the actual infinite sum? Well, that means I'm interested in the 10th remainder. This is the error if you only add 10 terms. This is the actual error that you have if you add only 10 terms, not an estimate on the error. This is the actual error. So if you calculate this, you know exactly how far you are. But we're not going to calculate it. We want to estimate the error. So what do we do? We know this guy is less than the integral from 10 to infinity, is it? Yeah. Of the corresponding function. We know the 10th error, so only adding 10 terms, the 10th error is going to be less than the integral from 10 to infinity. That's the whole deal. That's the only thing we need to know. Well, okay, if it is, and this only works for, positive, decreasing, continuous things. Because remember, we're talking about this left end point, right end point being over and underestimate. That only works if it's decreasing and positive and continuous, so you can take an integral. Okay, well, what is this? This is x to the minus 3. So that's x to the minus 2 over minus 2 from 10 to infinity. Yeah? So at infinity it's 0, so we don't really care about that. And then it's minus a half of 1 over 10 squared. Right? Is that right? Am I doing this wrong? No. So that's 1 over 200. Which is like 5 over 1,000. Right? Is that like this? So that's 1 over 200, right? Which means my error from the actual answer is at most this big. So this number I have here, it could be this plus 0.005, so there could be a plus 5 here or a minus 5 here, but between that range is my actual answer. So all we're saying is the error is at most that much. Oh, you're right. So I mean, you can use both sides of it to get a really good estimate of precisely how much. Actually, let's do that. So we know the error is at least, so this is kind of weird. It's saying, we know we have an error from the actual answer, but we can also actually figure out at least how much error we definitely do have. sort of weird. Why would you want to know how much error you're definitely making, rather than what is the maximum amount of error you're making, which would be something more meaningful. This is like saying how much error are you guaranteed that you are definitely making by only taking 10 terms. And that's just the integral from 11 to infinity of 1 over x cubed dx. Same function from 11 to infinity. So it's plus 1 over 2 times 11 square, which is 1 over 242. So our error is at least, so it's not really a minus. So doing the estimate on both sides shows you that you're somewhere between this much and this much off from this number. So to this number you have to add some number between 1 over 242 and 1 over 200, and your actual infinite sum is between in that range. Right? So in fact, so what does this mean? It means the 10th sum plus 1 over 242 is less than or equal to our infinite sum, the sort of holy grail, the thing we're after here. I think we get all the way adding everything to infinity, and that is less than or equal to this 10th sum that we got, 1.1975 plus 1 over 200. So you know your sought after answer is in this range. That's what you know for sure. It's not too big of a range, right? This is 0.005 and that's something. So now let's suppose I said, how big do I need to go? I went to 10 terms here and I got like, maybe the first 2 digits are for sure what they are. Say I want my error to be less than 0.00001 or something. Say I want this error here, this error was less than 0.005. Say I want it to be less than 0.0001. It's like a much better estimate. I want 3 decimal places of accuracy. You want to use more terms, but how many terms? That's the question. So what should n be? So this is the kind of question you get on the exam. This is the kind of question last time we had on the exam, which is how many terms do you need? Do you need to get an error less than 0.0001, say? Sorry? Yeah, it's in this range. So for the maximum error, you should just use the right one, because this is the bigger of the two. No. It's the actual sum is between these numbers, right? The actual sum is between these numbers. So if you want, you can take the average of these two values. That number is somewhere between these two values, right? And then you know from that average point, you can do some tricks to this. You can say, well, I can take the average of these two, that's somewhere in between. Then from that average to here, the difference is at most the average of these two values. Or something like that. But generally the safest thing to do is to say, look, we know that the nth error is less than the integral from n to infinity, right? This is how you're expected to solve this on the exam. At least here. So we know the nth error term is less or equal to the integral from n to infinity, we want the nth error term, so we know this, and we want the nth error term to be less than 0.0001. So how do we achieve that? Make sure the integral from n to infinity is less than 0.0001. Because if that integral is less than that number, we know our error is less than the integral. Error is less than the integral is less than this. We get our desired result, right? And so let's see, how do we make sure this is less than 0.001? Well, so it's the same, so we'll not worry about this side now, but we'll say we're talking about the nth guy, that's less than the integral from n to infinity, which is the thing here with n instead of, so it's instead of this, it's 1 over 2n squared in general. And how do I make sure 1 over 2n squared is less than 0.0001? Just solve for n. Take n on the other side. So this is what? Is it 10 to the 4? 10 to the 4, right? 1 over 10 to the 4.
What would you call this?
So I want 1 over 2n squared to be less than 1 over 10 to the 4. So cross multiply this. So I want 10 to the 4 to be less than 2n squared. Yes? Can everyone do this kind of manipulation? And then, so I want n squared to be more than 10 to the 4 over 2, meaning I want n to be at least 10 squared over root 2. 100 over root 2. Really?
Square root of what?
100 over root 2?
Why didn't he square root 10 over 2 over 2?
I mean, yeah, that's exactly
No,
true.
square root of 2 is
70.71. So by this estimate, it looks like if you took 71 terms, you'd get to between 0.0001. It's probably not the best sort of estimate.
Remember, it's a the exam. You have to do 100.
Oh, okay, that's good.
You want to do
In my notes, I was only going to 0.005, so I thought it should be a smaller
just
number. But yeah, so if you want to get to 0.001, 71 terms should. So, it should be something more than 70.71 terms. So you should take 71 terms. Right? So just, how do you estimate how many terms do you need? You use this part of the estimate. You know the error, this is the error after using n terms, is less than this integral. Make this integral less than the 0.00 whatever. Solve this integral, solve for n. It tells you n should be bigger than a certain number. That's how many terms you should need. This is always how this is done. Okay? Yes. We have to take 71. No, because n is bigger. N is an integer which is bigger than this. So you can't take 7. Okay. So now you have all the tools for the quiz on Thursday. Again, this only works when the function is positively increasing. So let's do a couple of examples of this sort of integral test. Oh. You talking to me? This series. Series.
Like this, back in school, we used to do more than so we used to what the money for you understand how it calculates and this is very
and then some non-examples. Okay, so let's try to see what we can say about these using the integral test. Okay, so the first one, 2 over 5n minus 1. So, is it divergent? Right. Yes. So, can you use the integral test? Yes. So it's continuous. Right. At 1 over 5, which is luckily less than 1. So from 1 to infinity is fine. And so it's continuous from 1 to infinity. It's not continuous at 1/5, but that's outside of 1 to infinity. And so it's not continuous where the denominator is 0. It's positive. Are all these terms positive? Can you just look at them and say they're positive? So generally you have to check, right? You can't just look and say, it's positive. You have to check. This is the thing positive. And this one is, n is bigger than 1. So this thing here is bigger than 4. So some number divided by a number bigger than 4, so that's positive. It's decreasing now. Is it decreasing? Yeah, the denominator keeps increasing as n increases, so this thing will decrease. So it is positive, continuous, and decreasing in 1 to infinity. So you can compare to the integral of the corresponding thing, 2 over 5x minus 1 dx. So you change the n to x from the same spot to the same spot. Okay? So you can compare. It doesn't mean it will converge or diverge. It's just that you can compare. And then whatever this integral does, that's what the series will do. Okay? So a lot of people just assume you can use the integral test and then write, therefore it converges. That doesn't mean that. And then this integral is what? It's the what of 5x minus 1? Yeah, log. So it's 2 log 5x minus 1 over 5 from 1 to infinity, and that's infinite. So it diverges. Or if you want, you could have used direct comparison and said, wait, can I use direct comparison? No. Oh yeah. because that denominator is bigger, so it's smaller, and this is divergence by p-test, right? Which is what he was saying. Diverges times p is 1. So either way it diverges, therefore this diverges, right? Okay, what about this one? So what is the series here? N? Why 5n? Okay. Okay, that's maybe, it's like a roundabout way of getting where you're trying to go. So you're saying 5n minus n plus 1, which in other words 4n minus 1. Because it's, you have to see, you're adding 4 each time, right? So it should be a 4n. And it's minus 1 because the first one is 3. Right, so just by seeing that it's going plus 4, plus 4, plus 4, plus 4 each term, you know it should be a 4n. Be 4 times something plus 1. Or if you like, this is just 4 minus 1, this is 8 minus 1, this is 12 minus 1, and the next would be something minus 1. So it's always, it's 4 times 1 minus 1, then it's 4 times 2 minus 1, then it's 4 times 3 minus 1, and so on. So it's 4 times n minus 1. Yeah? So this is the series, if you like, which is for n minus 1 from 1 to infinity, and much like this one above it, it diverges by the integral test. Right? It's the same thing. It's decreasing positive continuous. Integral of 1 over 4x minus 1 is log, which is infinite at infinity. It's the same. 5n minus 1, 4n minus 1. You know, not much of a difference. This, on the other hand, is what? It's 1 over n root n, right? It's 1 over 1 root 1, 2 root 2, 3 root 3, 4 root 4, and so on. So it looks like n root n. N goes from 1 to infinity. That's another way of writing n root n is what? 3 over 2, or 1.5. So that converges because by p-test. Okay, what about this? Cosine pi n over root n. So for now, I just want to say, so first of all, can you apply the test, the integral test? Yes? No? Which? Yeah, I mean, what is cosine positive? Or yeah, it's cosine goes up and down like this, so it's sometimes positive, sometimes negative. So obviously it's not. So we cannot compare it to the integral. Yeah, cosine is sometimes positive, sometimes negative. In fact, cosine pi n is just minus 1 to the n. It's minus 1 plus 1, minus 1 plus 1, minus 1 plus 1. So it's sometimes positive, sometimes negative. This series, you can also write it as minus 1 to the n over root n. In other words, it's 1 over 1 minus 1 over root 2 plus 1 over root 3 minus 1 over root 4. So it's definitely, so we just can't use the integral test. Okay? Cannot use integral test. What time is it? Okay. And this one? Now it's square of it. So it's positive, so at least it's not. Is it decreasing though? Why is it decreasing? Yes. Uh-huh. Yeah. That's not true. I mean, what you said is true, but it's not decreasing, so you can't use the test. You can't use integral test as is, because it's actually technically not decreasing. It looks something like this. You have a it eventually is becoming smaller and smaller, and eventually kills the cosine, so to speak. Cosine wants to do this. When you divide it by a bigger and bigger number, it becomes smaller and smaller and smaller. But it's still sometimes increasing for a little bit and decreasing, increasing, decreasing, increasing. It never is decreasing, decreasing. You know? So you can't use decreasing. Yes? It needs to be monotone. In fact, more, it needs to be decreasing, not increasing. Okay, so that brings us to the next thing here, which is that basically just like we did with the for series like this, you can use the direct comparison instead. So instead you say, look, we can't use the integral test, and we have this cosine square of n. If it was n pi, then maybe something could be done, but it's n, and that's unpredictable. No, actually, let's take this, something like this. Is that what I had? Yeah, 1 plus n squared. If I have this series here, every term is positive, and every term, each term here is less than 1 over 1 plus n squared. So just like we did with integrals, we say we have a positive thing which is less than something else, and the something else here converges, and because you're less than something that's finite, you must also converge. This is the direct comparison test. This is the DCT for series of the direct comparison test, which is 11.4. Checked you to starting the next section in the last 10 minutes. Yes. Oh, you could do more. Yeah, you could say then by more direct comparison, this is less than 1 over n squared. which converges by p-test. Or you could just immediately go there. Yeah, in the exam you have to use whatever test you can that applies. So DCT, direct comparison, limit comparison, alternating series test, ratio test, root test, whatever test, integral test, divergence test. You have a bag full of like 10 tests, 8 tests, and you just have to see which one applies to this series, use that one. There's maybe more than one that applies. So direct comparison test, which says if you have ANs are all less than BNs for all n, then the series AN diverging means the series BN will diverge. But the bigger series converging means the smaller series will converge. So just like with integrals, if you have a bigger thing that's finite, the smaller positive thing must also be finite. Or if your smaller thing is already infinite, the thing that was bigger must also be infinite. It has no other place to go. It's like the most reasonable statement. Right? So does this series converge then or diverge? It converges by the direct by DCT, you would say. Right? Instead of. So by the way, did everyone sign?
Yes.
Where is the thing? Keep passing it. What time is it? 5 minutes? Okay, so hopefully it will get to people. Yeah, so this direct comparison is used just like we did with the integral test. Anytime you see a cosine or a sine, you know it's between -1 and 1. Anytime you see an arctan, you know it's between -2 and pi/2. Right? Any positive thing you can always delete, make it 0 and get something bigger. I mean, smaller. So, like sum of 5 over 2n squared plus 4n plus 3, something like this. You want to make the denominator smaller, so it looks like 1 over n squared. So it looks like it should converge, right? It's the same intuition. You look at it, it looks like 1 over n squared. You think that looks like it might want to converge.
No, you don't.
Because it wants to converge, I want it to be less than something
have to
bigger
go to them, that's
that
right.
also easily
Okay.
converges. Right? If you want to say something converges, you want it to be less than something that also converges. And it's obviously positive. So it's positive. And how do I make it less than something? Well, I just drop the extra terms in the denominator, because dropping these terms and dropping something positive, making the denominator smaller, thereby making the quotient bigger. So this converges by p-test. As p is 2, which is bigger than 1. So similarly, you could have, we could do the series log k over k that we did before. We did it using direct comparison, but we could also use, we did it using integral test because it was decreasing in positive and whatnot. But we could also have used comparison because it's bigger than the series 1 over k. The log of 1 is 0, but log of 2, 3, 4, they're all bigger. At least from 2 to infinity. And this one diverges and is positive. So the bigger thing, so the smaller positive thing diverges, the bigger thing must also diverge. Okay? So now if you have something like n over 2 to the n minus 1, this direct comparison test is really useless, because at least directly, because what do you want to do? You want to make it looks like it should directly converge. It's much bigger, 2 to the n is much bigger than n squared and 2 to the 4. So you want it to be less than something, but to be less, I have to make the denominator less. I have to make it smaller, so that the quotient becomes bigger. But if it's already minus 1, I can't just take away the minus 1, that will make it the other way. That make it bigger, but how does minus 100 help you if minus 1 will? Okay, but I still have to minus 1 in the denominator. How? Why is that? That's the whole question. I mean, you would get it's bigger than n over 2 to the n, which converges. But something smaller converging doesn't tell you the bigger thing converges or diverges. So we really need it to be less than this. So instead, here is where you do the limit comparison rather than the direct comparison. You say, I don't know if it's greater or smaller than anything. I'm not sure, but it sure looks like just n over 2 to the n, or even 1 over 2 to the n. It just looks like 1 over 2 to the n. You just make a bold claim like that. You say, look, this series, I don't know if it converges or diverges. I don't know if it's less or more, or if it's going to make a plus minus here in the denominator, you're going to make it less or more. Don't care. It looks like 1 over 2 to the n. So for that, you just compare it to another series. That's called limit comparison. And how do you do it? Yeah, you have to take the limit of the term. So we'll do that next time. What time is it? Are we on time? So next time we'll do limit comparison, which is